Awesome. All right, let me move on. B9, right? So B9 asks us to calculate delta G for the reaction of NO plus O2 gas plus 2NO2 gas. So we can just simply use the thermodynamic info at the back. We can just simply use Hess's law, right? So if we have the delta G of this reaction, in this case, what we get is, right, so we're going to have 2 moles of NO2, right? So it's going to be then delta HF not of NO2 minus, right, the number of moles of delta HF not of NO plus the number of moles of delta H, or not delta HF, sorry, delta G. Gotta pay attention. Delta GF, delta GF, O2 in this case, right? So we have all of those things, so we can just simply look up the values, right? So we're going to have 2 moles of NO2 that's going to form in this case, right? So we have 2 moles in this scenario, right? And the delta G value for NO2 gas is 52 kilojoules per mole minus, right? And so now for NO, right, we have 2 moles of that as well. So we have 2 moles of that times the value of delta G is 87 kilojoules per mole plus 1 mole of O2. And then without even looking, I already know it's going to be equal to 0 because it's the elemental form, right? So it's 0 kilojoules per mole. And so what we get is moles cancel everywhere. So we plug that in. And so what we get is 2 times 52 minus 87. Oh, 2 times 80. Sorry. 2, right, let me just pay attention. 2 times 52 minus 2 times 87, right? So that comes out to negative 70 kilojoules. Delta G not of this reaction is equal to negative 70 kilojoules. In this case, right? That matches pretty closely, right? I have negative 68.2. I must have used probably a different equation when I was originally going through and doing that right there, right? But those are pretty close, right? I mean, it's just rounding up. So, right, so that's how you get the delta G value in that case for that right there. I may have, I think, originally like went all the way around and just simply done the whole like delta H and delta S stuff as well, and then just simply used those equations. But you can just simply use the delta G stuff, right? You'll get pretty similar values, as I think I already had shown with B2, I think so. Part B, calculate the equilibrium constant, Kp. How does this value match the Kq calculated in B8D for the reverse reaction, right? So in this case right here, we already know what the relationship is between delta G and K, right? So we have delta G naught is equal to negative RT natural log of K, right? And so the K in this case, right, because it's a gas that we're looking at, is going to be Kp. And so we're trying to get to what K is. So all we have to do is rearrange all of this, right? So natural log of Kp is equal to delta G naught over negative RT in this scenario, right? And so then to get rid of the natural log, all you do is just simply take the e to the power of for both sides, right? And that gets rid of the natural log. So then we get Kp is equal to e to the power of negative delta G naught over RT, right? And that's how we get that part right there. So all we have to do now is just plug in our numbers. So we have e to the power of negative, and so that's what, negative 70 kilojoules over RT, right? And so the R, again, has to be the same scaling. So let me just go ahead actually and then correct that right there. And so instead of it being kilojoules, I'm simply going to put it as joules in that case. And so R is going to be 8.3 joules per Kelvin times 298 Kelvin. And so Kp will equal e to the power of negative times negative 70,000 divided by 8.314 times 298 Kelvin, right? Comes out to 1.86 times 10 to the 12. And that's here, which is pretty close, right, to the 9.01 times 10 to the negative 11 that I have right here, right? I think, you know, the slight difference, right? So if I use the value of the negative 68.2 that I have up there, 68,200, right? That comes out exactly to that right there, right? So it's the same equation, it's just slightly off just because it's slightly different delta G values, which is always one problem, right? If you're scaling and having things scaffolded and you have to do the right, you know, math for one part, for things to properly match up because things get kind of messed up. So anyways, but that's right. So that's how you calculate B, right? And so it comes out to 1.86 times 10 to the 12. And so if you already did B8D, right, and you take simply the inverse of this value that we had gotten here, right? So the 1 over 1.863 times 10 to the 12, right? That comes out to 5.36 times 10 to the negative 13. That's pretty close to the value, right, that we get in B8D. So, right, and the difference is, right, if you look at B8D, it's just simply the reaction, but in reverse, which makes sense, right, in terms of then why you can flip those values in those cases, right, where you can take the inverse of them because it's the inverse reaction. And so that's the relationship there and stuff. So, part C, determine the direction the reaction would proceed when 0.3 atmospheres of each gas are introduced into the reaction vessel. So what we're doing now is we're going to calculate what Q is. And once we know what Q is, we can compare that to what we know the value of K is, right? And then if the value of Q is less than the value of K, then that means that you have to form more products to get to equilibrium. If Q is greater than the value of K, you have to then reverse the reaction and, you know, and generate more reactants to form to get to equilibrium in those cases. So what we're going to do now, right, is we can just simply calculate, right, what Q is. So again, I'm just going to write out what the equation is right here just for myself, right? So it's 2NO gas plus O2 gas yields 2NO2 gas in these cases. So we have all of these right here. And so then Q in this case, right, is just simply going to be the partial pressure of NO2, right? And that's going to be to the power of 2 because, right, it has the coefficient of 2 in the equation divided by, you know, the partial pressure of NO gas. And that's going to be to the power of 2 as well, times the partial pressure of O2 gas in this scenario. Right, and so now we just plug in the value. So all of them are just simply going to be 0.3. So we have 0.3 atmospheres squared over 0.3 atmospheres squared times 0.3 atmospheres in this case. So we do the math here. So what we get is, I mean, basically, right, I can just make my life a lot easier, right? These are going to cancel out. So it'll just simply be 1 over 0.3. So 1 over 0.3 comes out to being 3.33 in this case. Right, so 3.33 is a lot less than, you know, 9.01 times 10 to the 11th, or whatever it was, 1.2 times 10 to the 12th, I think that I had gotten. Right, and so Q is a lot smaller than what K is, and so that means then that you have to form a lot more products to get to equilibrium, right? And so that's why, right, at this point in time, right, you know, you're going to be, you know, forming products in this case, right? Product formation is favored at you know, those pressures for everything. So then the final question is,